Okay, how are you? An operating system has components. One of the components is CPU scheduling. That means the memory management. There are a number of processes that one use to memory, and to efficient usage of memory, the duty of one of the operating system is manage this memory for each process according to different scheduling algorithms. Here to show, I want to show you one of the algorithms. One of these on this slide. I show you what is the shortest job list algorithm. How we work with a process which has execution time including IO burst. Means yes, process has number of operations, computations, and accessing input output. Without input outputs, what cannot be completed. So when one process want to access output or inputs, it stops, for example, the processing unit. So in this case, the operating system prohibits this process from the CPU area in order to get the input request or output request, and then after the completion of the request, then it will come back to the previous stage or process stage to take as remaining execution. So this is minor. This is basic way. We are ignoring this thing and simply calculating only a single burst time case. We did this in more on different videos, but this is not. These are a simple assumption. Even here, putting IO1, IO2, this is only a simple assumption also. There are number of IOs are there, means number of input accepting stages, there are number of calculation stages are there. In for simple understanding, here I take first assume that first executions are there. After some execution is need input output request. Then after that completion means for this execution, this IO request is as input or as mandatory or as a prerequisite. And then after next, it's also go to the next. It might lead to the system or take next further of requesting or IO access. So in this video, I show you simply to explain you how can we calculate for shortage of burst algorithm. If you are given such type of detail, means a process with a variable time with a number of burst time. Take here BT1 means burst time 1, IO1 means input output request 1. It's the same thing, the number means is a request bit BT1, BT2, I1, I2, other time. The request, what we do is to calculate turnaround time or duration in the system, waiting time without any execution. The IO request included in the waiting time is because it's out of CPU. Okay, then CPU utilization. Is there any idle time in the CPU? That is, we calculate for SJF and for the others, but in this slide we calculate only for SJF. Okay, to have simplify my video size and my time required, I primarily built a number of situations. Means nearest explanations I put timeline including for this shortest job is based on the given data. And timeline 0 as you see here, and the timeline 0 means and the first time which process is in memory, which is process A that requires total burst time of. You have to add all timeline, means all burst time, means there in the middle IO request is there also IO request is there, but you have to first see amount of the execution time for the given process to be the sum of all burst time or the sum of all execution time or service time in here. So for when starting to calculate for E, we take the all burst time is given, which is 3 plus 4. So A now requiring at start at time 0, A need 7 CPU time to complete S execution, even if there is middle remaining IO requests they may leave at last time, but total of CPU time this process A require is 7. but its first execution is go on 3, because after the completion of 3 units, it must be the IO input out request or accessing that may be further input for the next process of mass execution. So that's the timeline I prepared here is first in the initial time at time at time 0, process in the memory is A only. So now I show to Gantt chart this. Using Gantt chart here, I used this SJF calculating TAT ability utilization to have to create a Gantt chart in 2 cases, which is in the first case I have to first I have to create this Gantt chart for CPU execution, and also I have to create the Gantt chart for IO utilization. Unless I cannot get real answer, I cannot simply complete my work. So here I completed in each stage. In the first, A starts work since A need 7 units, even if A need 7 units, but A only can continue execution 3 units only, since after 3 years completion they have to get the IO access. So that's the first execution is from 1 to 0, then equal to what? Equal to 4 next 2 units for IO request. So 24 hours. So that A go to the IO request, but IO request initially is idle under the completion of A. So at time 3, A leaves the CPU and enter into the IO request. Let's continue the number of executions IO request, but at timeline 3, since SJF is non-preemptive, means once the process starts its execution, it continues unless it's rejected by itself, such as IO request or completing this execution, unless no other process can reject this process from executing. So that SJF is non-preemptive executing algorithm. So a complete is a first 3 units and then enter into the IO request there, which process take first and time and CPU at time 3. Before do this, we have the timeline. We have to create timeline. At time 3, while a process in the CPU, while a process in the ready queue, not CPU. The CPU is now is idle now. It's left free now. So when you see the given, there is the arrival time. A arrived at time 2, no, B arrived at time 2, and C arrived at time 3. So that when A leaves the first execution, complete a first execution and leaves the CPU, those process B and process C are the ready queue. So that B need a total of 6 units. Means adding here is first one is 4 units and the second one is 2 units. So adding we need 6 units of execution time. C needs 3 in the first and 4 in the next. So that total of 7 units. So C needs 7 units, B needs 6 units. Which one is the shortest job? B is shortest job. Yeah, B is shortest job, so that B continue take place. We can continue until its first IO request, means 4 units continuously. So from 3 to 7 B take place, and after 7 now see we want to execute IO input request, so that at timeline 7 the CPU feed, so we enter into the IO request. There is initially from starting 3 and using 2 units of the IO request according to the given, and then we left the system, so that at time unit 5 we left IO request and wanting the CPU time. But now the CPU is left or freed at time unit 7. So at time unit 7 we take a scheduling, even if A left the system at time unit 5. So at time unit 7, which take place at time 7, what a process in a ready queue we have to see is at time unit 5. Initially process C is there, who is requesting 7 units, which is starting from timeline 3. Next process A is there. Before A, or which one is first arrived? There's the same thing. The also arrived at 5. A also rejected from or left the processing or IO casting and need the next CPU time. So at the same 5 units, but D is without any service time. So C is first really asking. So C needs 7 units, D needs 3 units, and A needs 4 units at time 7 to take place here. You comparing this, 3 is less than another, so shortest job is D. But D can execute only 2 units, which means the first execution, then go after 2, go to 3 unit to IO request. So among 7, 3 and 4, 3 is less than, so D take less for 3 units accessing 7 to 9 is D here. Be choosing in IO from 7 to 8. I think there is given 1 unit only. Yes, 1 unit or only IO request. So we left at 8 IO request, but this will be free for this time since the left or the completes first execution at main and then go to IO. Now B is in a ready queue before completion of the yes. So a timeline name, okay, a timeline name, which process or which what a process in this ready queue is. C initially started at 3 is still there. A started from time 5 and still there, and again new process arrived at timeline at time 8 joined to system requiring 2 units only. Initially B needs 6 units, but all 4 units executed in the first request, and now remaining of 4 units for B is 2 units only. Since comparing the shortest job 4, 7, 2 is the shortest, so B take completed its execution. So at times name B take place. After completion is CPU time at 11. Is B leave that system or go to IO request? Yeah, we go to IO request. So you need IO request there after completion of second bit request. So B now leaves the CPU time at 11 and enter into system starting from 11. Yeah, starting from 11. But B still in the system until 10. So 1 unit waiting there for IO request also in case of B, because they are allowed or they want to access first IO 3 units. So 3 units means starting from 9 to 10, 10 to 11, 11 to 10, 3 there, but B is waiting to access 1 there, but they are there. B is still in working, B is waiting for B, but 2 processes now are there at time 11. At time 11, they are process C and A only there. C and A only because of what? B left, leave the system already completing to needs only IO request. D is still there, not arrived. Yeah, D is not arrived at 11. D is not arrived at 11. So comparing C and A is smaller than C, so A completely executed is a second bit is then no IO request also, so the chance for the E taking it 11 to 4 units means adding 4 to this is 15, so we can delete the system as units already left. But at 15, what are pros in the ready queue? What are pros in the ready queue? 15, the good chance of accessing IO achieved and executed also did 3 units of IO request and completed and leave the system. So this 15 taken as B's completion time. The completes first IO request and leave the system active, and now want to update next execution, so that now memory or CPU want to take other or ready to take other process at timeline 15. So what that process and ready we accessing that. C still there is no chance to get, but new arrival at 10 means leaving the IO request, and now they want to take the next CPU time of this D is there. So comparing this C and D, D is very small, so they take a place. the take place after the completion of A at 15 take place, then the complete 1 unit. Yes, this 1 unit only. Yeah, 1 unit only to the expression after at 16 at the completion of 1 unit of discrete time. They leave the system or not? They cannot leave the system since it has 4 units of error case there. So we enter into the error case after 16. Starting from 16 to any the easier and now access error case. So now the time is for C. At time 16, it's not 15. Mistake. Yeah, that in this comparison is correct. Time 15, we take chance, we take the comp. Now, remaining after time in 16, what the process in the system is only C is remaining, but still no go any accessing. Any accessing cannot, they do not add it to this process. The chance to not given. So, first CPU request for C starts at 16. From start 16 and the other first the length is 3 units, so from 16 to 19 means 16 to 17, 17 to 19, 8 to 19. See take first I request, no CPU request. After this she has 2 units of I request, so but she need to take place here at time 19, but this isn't completed until this time, so waits for 1 unit of time and then to take after 20 to 22 to input our request, then back to the CPU. So no other process in our system, no other process remaining, no other process in the radio queue, so CPU being idle for 3 units. Here is a little mistake. For 3 units, CPU being idle means from 20 to 22, from 20 to 22. No, it's not change 2022 until the C complete until C completes its first, until C completes the first IO test. That's that I make this one to indirect clearing. That's taken as CPU idle time. The CPU idle time is from 20 to 22. Where you see that from 20 to 22. Yes, it's 19 to 22. 19 to 22, not 20 to 22. 19 to 22. That's 3 units, yes. That's taken as CPU idle time. CPU idle time. So after completion D, we get 20 and 2 units of the first I request is there, and so as now 2 units, now we get next bit request for first time and then leave it and for the resolution. So this is the last C is the last process to lead the system. This I request is idle after the completion of C request. So this Gantt chart for CPU term and this Gantt chart for I request. You have to take your own work and complete these results. You have given questions there. You are required to calculate the time that is TAT and WT. So you can complete by yourself first. Then compare with this answer. So what calculation can be? What's the completion time of A? Since this is equal to completion time minus the arrival time. You know that is equal to completion time minus arrival time of the process. So what the completion time for A is 15. What the time for A is 0. So it is equal to 15. As completion time for B is here, you take this one, not this one. You have to leave this because the duration of the process, including the I axis. Okay, so 15 or so for B minus B's arrival is 2 units. That is 13. For C, you have seen is the last process to be the system, which is 26. The arrival for C is 3 units. We have this one is 23. For D, this leave the system here. He leave the system here. Yeah, at 20. That is all my new figures here. This also expensive. That's where the leave the system is. That is how the system after 20. So this mistake 20 minutes arrival time for these 5. Okay, so 10 minus 5 is 15, is 15. Okay, after this data, you are doing this, so what total burst times for initially A 7, B is 6, C is 7, D is this is start, where is this start? This start here 3. Yes, so that is 8 minus total burst time dt total, yes, means total since this is our frequency. So state of A is 15, total of A is 7, so subtracting this is 8. We get this chance correct. It's correct. Maybe for this mistake as well. It's correct. That's 10. Waiting times for this tail is simply 3. As we got here, this means 7, 16. So what's the speed percentage? As you see here, as I do 3 units is I do, total of 6 units. So what the remaining formula we can get is 23 or 26. Multiplied by 100, you get the approximate value of 80.46% each side. So this is how we can calculate for first come, first row, no, the short row first. Next, I show you in the next video. I show you how to calculate the other elements of our system many time next with the highest primitive version of scheduling algorithm. Then also RR, also the same to highly primitive version of algorithm. The scheduling algorithm. I show you in this video this thing for this. Bye.